and welcome to Top of the Flops, a rundown of the most popular experiments that tend to go wrong for teachers. In this programme, we'll show you what happens when things don't quite go according to plan and give you some top tips on how to make them go right. I've come here to Cleves, the school science support service, to meet three chemists who'll be guiding us through our chart.
Cleves runs a helpline for teachers and technicians to ring in with any problems that they've got, things they need to find out about. And what we've done is we've had a look at the records of all the helpline calls that we've had and picked the ones that we get the most helpline calls about.
Many experiments teachers think are possibly banned, but indeed they're not. They can do them all with proper training and practice.
We're going to show you how to do things correctly and safely.
Excellent.
And still get a lot of enjoyment out of it.
We're conducting these experiments under carefully controlled conditions to show you what happens when they go wrong. So we don't advise you to recreate them. As well as the right methods, our team will be showing you some alternative approaches to some classic experiments. At 4, it's tricky, it's nylon rope. But make sure you get the mix the right way round.
Nylon is made from two chemicals. This one is a solution of something called 1,6-diaminohexane in water. And that one there is sebacyl chloride.
So what is it that goes wrong then, commonly?
Right, the most common error is getting the two layers the wrong way around. We need to pour our aqueous solution in of the amine first. And then you pour the sebacyl chloride in, the organic solvent, on second.
And this is what could happen if you add the solutions the wrong way round.
What we've got coming off is hydrogen chloride, and if I just put
Wow.
that, it's pretty unpleasant.
That's a really violent reaction, so I mean students could quite easily make that mistake.
Probably the most common one is where you've had groups of students doing it. They do it with quite large amounts, and you get a class full of hydrogen chloride fumes, which you can see
reaction, actually.
Yeah. I'm going to get you to put a pair of gloves on. And these are nitrile gloves, so they'll protect you from splash.
OK.
What we need to do now is pour solution B so that it forms a layer on top of solution A. And the reason why you do that is that when the two layers come together, because the organic layer is over the aqueous layer, it traps it and the hydrogen chloride dissolves in the water.
Underneath.
Yeah.
Straight away?
Try with the glass rod. And you need about the same depth again. OK, you can see it's already starting to fume a bit because the two chemicals will start reacting quite quickly. That's it, keep going. And then you should be able to wind out a rope of nylon. And where the two chemicals meet in the middle, that's where they react. You can probably come up to. Keep going. I have done this before and had nylon, sort of from one desk to another. It's actually a hollow tube that you've got, which is why you need the gloves, because if you touched it, all the chemical is still in there.
Wow. So that's how it should be done?
Yeah.
Number 3, the explosive nature of hydrogen.
We get quite a few hydrogen explosions reported to us, and this was an experiment that was reported to us by a school. All it is its usual way of generating hydrogen, so we've got some zinc metal in the bottom, and we're going to react it with some 1 molar sulfuric acid.
Copper sulfate solution will act as the catalyst.
OK. What you should do is collect the hydrogen and then test it well away from where it's being generated.
OK.
Because hydrogen, oxygen gives you an explosive mixture. But what we're going to do here is actually test it just above where it's being generated.
Oh, OK. So the same vicinity.
Yeah.
Which is where the problem lies.
Yeah,
okay.
And that's what's gone wrong before. So I think for this one, I'm going to ask you to step out and I'm going to ask Bob to come in and give me a hand.
I shall retire to a safe place. The wrong way to test for hydrogen is close to where it's being generated.
try again, because there should be some hydrogen coming out into the tube now.
Sometimes when you try to get something to go wrong, you can't.
It's not going to work.
Safe to come back?
Yeah.
Yes.
Thank you, Bob.
OK, thank you.
Well, it didn't explode.
What happened? No.
No, it didn't explode.
What were you hoping would happen?
Well, the accident we got reported to us was a setup similar to this. And what the student did was he lit the hydrogen. He actually put the lighted splint close to where the hydrogen's being generated. What he should have done was moved away and taken the tube of hydrogen and tested it with a lighted splint well away from where the hydrogen...
the reaction's happening.
Yeah.
And so why didn't it work today?
I think probably the student just had the right combination of hydrogen and oxygen in the tube. Just perfect mix to give you a real explosion.
So today there just wasn't the right combination.
Yeah,
of
we're just
hydrogen
not
there.
good enough at getting it to go wrong.
Gosh, what can you do, eh?
Yeah.
A better setup has the reagents in a test tube. The hydrogen is collected by bubbling it through water.
Now, we really don't want hydrogen around when we're testing with a flame, so let's just move this away.
Having moved the apparatus away, we're able to test for hydrogen without the risk of explosion. At 2, only just missing the top spot, it's making chlorine gas.
One of the things that people do wrong is that they add the wrong acid to the potassium permanganate if they're going to generate chlorine using potassium permanganate. The problem is that people use sulfuric acid, concentrated sulfuric acid, instead of concentrated hydrochloric acid.
Concentrated sulfuric acid and potassium permanganate should never be mixed. The product is highly unstable and could react spontaneously. But we're encouraging a reaction with a drop of propanone.
It should ignite the propanone. So if you'd like to just...
And that's my job.
That's your job. just bring your hand away.
Whoa. Oh my goodness.
Yeah. So that's...
That's quite frightening. That was only a drop.
That was only a drop, and we've only used a tiny amount of the two chemicals.
Kleeps recommend generating chlorine by dripping 5 molar hydrochloric acid into freshly bought sodium chlorate 1 solution.
And then we just slowly drip the acid from the tap funnel into the solution. You see it's just reacting.
So that definitely looks green.
It's always a clue that you've got chlorine gas. If we just put the...
Definitely chlorine gas in there.
Yeah.
And our top of the flops is an old favourite, making copper sulfate crystals.
We get more phone calls about this through our helpline than any other because it's such a popular experiment and they do it very badly. Most of the instructions are rather brief in textbooks.
This method is one that is most often used but is fraught with difficulties and potential pitfalls.
Place 1 molar sulfuric acid into the beaker.
Stage 1 usually starts off reasonably well. The experiment usually begins to go wrong when students add the copper oxide. The first mistake is to add too much too quickly. So why do students tend to add the copper oxide too quickly?
Because they see nothing happening straight away and they just keep thinking, oh, we've got to add more and more to it.
So what should they be waiting for?
They should be looking for a blue solution to appear, but they're stirring it and it still looks black.
Having added too much copper oxide, the students are still trying to get a reaction.
They tend to stir very violently, like this, and they can upset the beaker.
Yeah. The suspension is now far too hot.
Oh, it's getting hot. Ooh. As it cools down, you'll see that it's spitting and and quite violently as well at times, and it can actually spill all over the bench and all over your arms as well.
So why is it spitting like that?
Well, parts of the sulfuric acid, or it's not sulfuric acid now, it's copper sulfate solution, underneath the unreacted copper oxide is actually boiling and expanding into a gas, and it just shoots the whole lot out. Yes.
Unfortunately, things don't often improve for stage 2 of the experiment.
So now the students need to filter the copper sulfate solution. So here's the filter paper, if you'd like to fold it.
Halve it and halve it again.
Yes. And then put it into the funnel. Now we've let it cool down far enough, we can now filter it.
So it's safe enough for me to touch?
Yes. Oh dear, what a mess. And now the blue solution's coming through, but all that solid goes into the filter paper and clogs all the pores in the paper, and the liquid can't find its way through.
This filtration process is now taking far too long. So how would you avoid that?
By not using so much solid in the first place.
Right, okay. Stage 3. The evaporation phase also has its problems. So what shall I do with that then?
Now pour that into the evaporating basin and place it on the gauze.
Okay.
And the instructions usually say that you should boil away half of the liquid.
Okay. This evaporating basin won't do the job. Ooh.
Oh dear. We've got a very small evaporating basin for the process. We should have used a bigger one.
Again, it's too hot. Whoa! Oh my goodness.
Well, that is known as bumping. There are parts of it getting superheated and it starts to boil very quickly.
The final problem is not keeping an eye on it and letting it boil dry, which not only spoils the experiment, but can also be dangerous.
The copper sulfate crystals have dehydrated to anhydrous copper sulfate. In a few cases, this can decompose further and produce corrosive sulfur trioxide and toxic sulfur dioxide, and the latter, sulfur dioxide, can affect any asthmatics in the classroom.
Oh, really? Measure 15 cubic centimetres of 1.4 molar sulfuric acid and warm with boiling water. Take between 1.9 and 2 grams of copper oxide and add half to the acid. Shake until the solid has dissolved. Then add the second half and shake again. A pleated filter paper is more effective than a folded one. The solution filters much more quickly. Boil the solution in a conical flask rather than an evaporating basin for 2 minutes exactly. As soon as the flask is cool enough to touch, pour the solution into a petri dish and watch the crystals form.
Oh my goodness me, that is fantastic.
It's beautiful, yeah.
That is really good.
So that's it. Remember, we've used carefully controlled conditions to make the experiments go wrong, so don't try and recreate those. But for the experiments that went right, we've seen that they can really enhance learning, tying together theory and practice.